Hello SlyFox community. In this video we are going to see how to design a 2.4 GHz PLL. Here you can see our phase-locked loop. I've used TSMC CMOS 180 nanometers technology, and in order to verify the performance of my phase-locked loop, I've performed transient simulation. And here is the results of my phase-locked loop. You could see the waveforms of V1 and V2. These are our oscillators, voltage controlled oscillators output V1 and V2. And here you could see that the lock time is more than 10 nanoseconds. You could see it. And here is our output. As you know, our VCO output is differential. We've created a buffer to make the output single-ended, and you could see it here. This is our single-ended output, and it is oscillating around 900 millivolts. And here is our input, which is an ideal clock. Now we are going to see how each block is designed and works. The first block is an ideal clock source. The low voltage is set to 0 and high voltage is set to 1.8 volts. This is the VDD for 180 nanometer technology. Rise time and fall time have been set to 1 femtosecond. Width is set to 200 picoseconds, and period is set to 416.6 picoseconds in order to create a frequency of 2.4 GHz. The next block is PFD. This is our phase frequency detector. Its inputs are our output and the ideal clock source, which you could see here. And after getting these inputs, it detects whether there is a phase or frequency difference or not and creates relative up or down signals. Let's take a look at internal circuit of our PFD. This schematic exists in Razavi's PLL book. It is consisted of two resettable D latches and a single AND gate. It takes the divider and reference as inputs. The reference is our ideal clock source, and divider, which in this circuit our divider is 1 because we have connected output to the PFD directly, so there is no divider. And our PLL is 1 to 1. And then it creates up and down pulses for us. Let's take a look at internal circuit of our resettable D latch. You could see our D latch is consisted of 4 NOR gates, and they have been connected to each other in this manner. Again, this schematic exists in Razavi's PLL book. Its inputs are clock and reset. If the signal is high, our circuit and output is reset to 0. And here is our output not here, which you can see it here, and we have called it Q. Now let's take a look at internal circuit of each NOR gate. You could see it is consisted of 4 transistors, 2 NMOS transistors and 2 PMOS transistors. NMOS transistors are in parallel, PMOS transistors are in series, and inputs are applied to the gates of these transistors. And here is our output node. Pop out, pop out. And here you could see how we should connect these blocks together in order to create a phase frequency detector. Reset pulse is created from here, which is the output of our AND gate, and up and down signals exist in these nodes here. Now we are going to take a look at the internal circuit and schematic of our AND gate. It is consisted of 4 transistors, 2 NMOS transistors in series, and 2 PMOS transistors in parallel. Inputs are applied to the gates of these 4 transistors, And in this node here, we could take the NAND. So far, we have created a NAND gate. In order to make it an AND gate, we need to invert our output so that we could get AND gate. And here is NOT gate. And as you know, NOT gate is nothing but one NMOS transistor and one PMOS transistor. Input is applied to the gate of both transistors and output could be taken from this node here. Pop out, and that's it for our PFD circuit. After PFD, our next block is charge pump. And as you know, the up signal must be inverted because this input is active low. And in order to activate it, the pulse applied to this node here should be 0. So that we need to invert our up signal, which comes from the PFD block, and then apply it to the up bar input. If we take a look at the internal circuit and schematic of our charge pump, I can explain it better. Here is our charge pump circuit. It is consisted of two keys, one NMOS key and one PMOS key. The signals are applied to the gates of these transistors. And as you know, in order to activate PMOS transistors, the gate signal must be 0 for digital circuits. So these are in fact nothing but keys, and the width of the PMOS transistor is set to 50 micrometers and length is set to 0.18 micrometers. For the NMOS transistor, which is a key, again the width is set to 25 micrometers and length is set to 0.18 micrometers. And after that, here is our current mirror, which creates a current of 100 microamperes for us. The width and length of these transistors is set to 0.425 and 0.8 micrometers respectively. The functionality of these two transistors is to create 100 microamperes current for us. This is true for the PMOS current mirrors as well. Their functionality is to create stable 100 microamperes current for us. The width and length of these transistors have been set to 2.15 micrometers and 0.8 micrometers respectively. And we could take the output from this node here. Pop out. And the current of our charge pump must go through a low pass filter in order to create voltage from this current, and then this voltage will be applied to control voltage of our voltage controlled oscillator. Here you could see the low pass filter, the value of resistor and capacitors. Pop out. And now we are going to take a look at internal circuit and a schematic of our VCO. Here you could see the LC tank, the value of capacitor, inductor, and resistor. This resistor simulates the internal resistance of our inductor, and the value of our LC tank is set in a manner to create a free-running oscillation frequency of 2.4 GHz. As you know, if the free-running oscillation frequency of our VCO is so close to our PLL desired frequency, we could get better results in our PLL or phase-locked loop. Here is our VDD, which is 1.8 volts. Here is our cross-coupled transistors, which creates negative resistance for us in order to neutralize this resistor here. The width and length of these transistors have been set to 250 micrometers and 0.18 micrometers respectively. Outputs could be taken from these nodes here. Here are our varactors. Their width is set to 200 micrometers, length is set to 0.18 micrometers. The control voltage is applied to this node here, and the tail current is set to 3 milliamperes. Pop out. And finally, in order to convert our differential output into single-ended output, we need to create a buffer. Now let's take a look at internal circuit of our buffer. In fact, it is nothing but a single transistor's differential pairs. Two NMOS transistors, which input is applied to their gates, and here you could see their width and their length. And here is the current mirror, which is also the active load for our circuit, and you could see the width and length of these transistors as well. And the output is taken from the node here, and the tail current is set to 1 milliampere. Pop out. And here is the complete schematic of our phase-locked loop. Now we are going to simulate our PLL. To do that, it's enough to click on this gear here to simulate your circuit. Nice. Now I'm going to plot V1 and V2, which is our VCO outputs. You could see them here. And our single-ended output. You could see our buffer is designed in a way to oscillate around 900 millivolts. And you could see the output of our single-ended buffer. And I'm going to plot our input as well, which is an ideal clock. If this content was useful for you, don't forget to give it a thumbs up and subscribe to SlyFox Electronics for more electronic contents. Good luck.